Abstractions are one of the best friends of programmers. When you open the Linux bash shell and you type ls pipe more, then the output of the command ls is being piped into more. But how does pipe knows to propagate the output of ls into more? Or maybe it's more that getting its input from the pipe, or the ls itself is piping it somehow directly into more. What is going on behind the scenes? Remember what we said at the beginning of this chapter, that the abstraction is one of the best friends of the developers, just like the dog is one of the best friends of the humans. In computers, everything is an abstraction. We don't really have programs. We only have electricity. And also electricity is some kind of an abstraction of an undergoing physical thingy that happens under the hood. Specifically, it is known as a well-known idiom in Linux that everything is a file. Why is everything a file? In Unix and Linux system, many peripherals are represented as a file. And remember how we said that the abstraction is one of the best friends of the software developer, software engineer, or programmer? This is because the file in Linux was chosen to be the abstraction that represents the peripherals. You could actually find some files in Linux representing the keyboard and other peripherals, the mouse. And you could write to them, or you could read from them, depending on whether the device is an output device or an input device. Choosing the file as an abstraction in Linux was a great choice, and in Unix. It was a great choice because a file is a very simple virtual thing that we can have inside our system. And what can we do with the file? We can read from it. We can check what is the existing saved data and just read it. And we can write to it. In many cases, reading and writing can also be presented actually as a screen. A screen, you read from a screen. It's a reading device. And a keyboard is a writing device. The printer is a writing device. The CD-ROM, if it's a read-only, is a reading device. So many of these devices are read and write. Why not represent them in a file? When you represent those devices and this hardware as files, the benefits that you get is that you have a specific and a uniform API to access them. You just access the files. So you can treat the screen and the printer as a write-only files. But instead of representing this information on the disk, you just display it on the screen and you print it to the printer. And the keyboard is like a read file, where you read the input of the keyboard from the file. So the concept of a file is a great abstraction. It is abstracting to us what actually happens, and we can use the same API for all this. In addition, we have managed to take some specific hardware and do an abstraction above it. Abstraction is what developers do all day. Whenever we mention a component, whenever we create a class, whenever we write a function, it's all an abstraction of processes. Because no one can understand the whole system and no one can understand everything. You cannot understand both gaming and graphics and hardware programming and server side and UI. So you use abstractions. And with these abstractions, you can work more efficiently. It will help you. When we say API, Application Programming Interface, in many cases you can treat it as an abstraction, because this API is abstracting from you the internals of what's happening behind this API. The same for the files. When we say in Linux that and in Unix that everything is a file, this is the abstraction of the hardware. And this relates also to what we said in the beginning of the ls pipe more. Because in Unix we have the concept of file descriptors. What's happening in Unix is that when you run a program, then when the program starts, there are 3 files opened. One is the standard input, also called stdin. The file number of the standard input is 0. And the second file is the standard output, also called stdout. And its file number is 1. This is the output of the program. The third file is the standard error, also called stderr, and its file number is 2. And this is the output error to the console. So when a program begins, we have 3 files already opened, already serving the program. 1 the standard input, 0, 1 the standard output, 1. And the third one is the standard error, also called 2. So 0 for input, 1 for output, and 2 for error. But when we say that we already have an open file, what do we exactly mean? Well, actually, when you call the Linux library libc and open a file, you get a file descriptor. You probably heard the term file descriptor. File descriptor, as its name is a descriptor of a file. Basically, the file descriptor is an index into an array of open files by the Unix system. The open files is managed by the kernel. And file descriptors are an index into this array of open files, which is handled and stored by the kernel. The kernel creates the file descriptor in response to an open file call. And it's associating the file descriptor with some abstraction of the underlying file-like object. It could be an actual hardware device or something else. This means that when the process reads or writes into the file descriptor, it is routed to the correct place by the kernel, to the correct input and output of the program. So the file descriptor is some kind of a gateway into the kernel abstractions of the underlying hardware. If you want to see where are the physical devices on the host which are described as files, you just do ls/dev. This is where you see all the files that are related to the hardware. And in Unix, they are also called device nodes. We can also mount file systems, and also there we use file descriptors and pointers and indexes. But we haven't answered yet what happens when you do ls pipe more. And this brings us to the shell. The shell is like a gateway into the operation system. But shells are not only gateways or terminals that you type command. You can spawn many programs, you have powerful abilities to redirect to outputs into inputs. You can create and run multiple programs simultaneously, and you can create scripts which are perfectly fine programs. And it all comes down to the fact that everything is a file, because in all these scripts and all this output and input, you are referring maybe indirectly to the files. So when you type ls pipe more, this is again the abstraction of the file. And why is that? Because the descriptor is pointing to an in-memory buffer. So remember when we said that each program that we run has 3 files? It has the std_in, the std_out, and the std_err. ls is also a program that we run, so it also has 0, 1, and 2. std_in, std_out, and std_err, and more is also a program that we run. The pipe which sits in between these two programs, the ls pipe more, is a buffer that is created by the kernel. When we do ls pipe, this tells the Unix system to take the output of the ls and put it inside the buffer. You can treat the pipe as a buffer, and it's really a buffer. And then the Unix system takes the output of the ls, put it inside the buffer, and the more is getting its input from the buffer. It's registering to the buffer. It will consume everything from the buffer. So you do an ls, you have a list of file descriptors, 0, 1, 2. You run the more, you have a list of file descriptors, 0, 1, and 2. And remember that we said that 1 is the std_out. So the result of the ls is at std_out, which is file descriptor 1. And this one is going by the kernel into the pipe, and the pipe is a buffer. And then in the program more, we have file descriptor 0, which is the std_in, and it's registering to the pipe. But the pipe is not a pipe, it's a buffer. It's a buffer of memory. And how do you read and write from a buffer of memory? With the commands, with the libc commands, read and write. So the more is reading from file descriptor 0, which is reading from the buffer, and the ls with the file descriptor 1 is writing to the pipe. The core concept here is that the pipe is a buffer. It's a memory that is being created by the kernel, and the processes are writing and reading from it. It's as if you have written a program to write to memory and another program to read from memory with the std_in and std_out. And everything right to the pipe is stored by the kernel until the other side, which is the more program, reads from the buffer. So you see how two little commands, the ls and the command more, are having file descriptors, which we said that files are an abstraction over hardware, an abstraction over input and output, and we have file descriptors 0, 1, and 2 for std_in, std_out, and std_err. And when we do ls pipe more, we just tell the Linux kernel that we want the std out to go to the buffer that it manages, and we want the more to register and to drain the buffer. It would simply consume anything it sees in it. So with that we have wrapped everything, because abstractions are the main tool of developers and are the best friends of developers. And you write them all day if you are a developer. You do them all the time, the abstractions. And the Linux system has chosen the file as the main abstraction, which is obviously a great choice, because you can write to it and you can read to it. And almost everything in computers is doing some computation and writing the output, getting some input, doing some manipulation and writing the output. And the files, you can read files and you can write to files. So with these basic concepts, we have managed to take two commands like ls and more and be able to see that using the file descriptors, we are able to consume from one of them, write to the pipe, which is merely a buffer that is managed by the kernel, and then read from the buffer with the next command. And with that, you can concatenate more pipes. So we have wrapped everything with this. So I hope you enjoyed this, and I will see you next time.